All right, let's take a deep dive into a paper that really shook things up. We're talking about AlexNet back in 2012. Before this hit the scene, image recognition, well, it wasn't exactly moving at lightning speed.
It really wasn't. This paper, though, it changed the game.
It did. Huge impact.
Yeah.
But before we get into all that, let's set the stage. What was the problem that AlexNet was trying to solve?
Basically, how do you get a computer to see the world, to actually
Right.
understand what it's looking at? I mean, think about it. Thousands of different objects, millions of images. And every image is different, right? Different lighting, angle, what's in the background. That's a lot for a computer to handle.
Yeah, that's a ton of information to process. So what was the state of the art before AlexNet? How were people tackling image recognition?
Well, there were some methods, like support vector machines. They were making some progress, but they had their limits. They couldn't really handle that level of complexity we see in real-world images. You need a model that's more like the human visual system, building up from simple things like edges to, more complex shapes, and then whole objects.
Okay, so that's where convolutional neural networks come in, CNNs. I mean, we hear that term everywhere now.
Exactly. And AlexNet, they really saw the potential in CNNs and kind of ran with it.
Now, I get the basics of CNNs, but why were they such a good fit for this problem? What is it about them that made them the right tool for the job?
It's all about how they process the information. They're designed to, well, analyze images in a way that's very similar to how we see things. They break down the image into smaller parts, then they extract features from those parts layer by layer, and ultimately they build up a representation of what's there.
They're kind of like digital eyes, scanning the image and piecing together what they see. But I remember reading that CNNs, especially back then, were really computationally expensive to train. How did the AlexNet team deal with that?
That's a great point. And that's part of what's so impressive about their work. They realized that these graphic processing units, GPUs, the things gamers were using, they could be harnessed for deep learning. GPUs are really good at parallel processing, perfect for the kind of heavy lifting that CNNs need.
So they were basically repurposing gaming hardware for cutting-edge AI research. That was pretty ingenious.
It really was. But even with GPUs, you still need a ton of data to train a model this complex. And that's another area where AlexNet was really ahead of its
They
time.
needed a massive data set.
Exactly. They used this huge data set called ImageNet. It's millions of labeled images, just a treasure trove of visual data. So you had this combination of powerful hardware, the GPUs, and this huge, rich data set. And that was a big part of why they were so successful.
Makes sense. But even with all that, I imagine there were still challenges, right? Like overfitting. I remember that being a big concern in machine learning.
Oh, absolutely. Overfitting is always a danger. It's like when you memorize the answers for a test but don't actually understand the material. The AlexNet team knew they had to be smart about it, so they came up with some really clever techniques, things like data augmentation and dropout, to make sure that their model could actually generalize to new images it hadn't seen before.
Okay, those techniques sound super interesting. But before we dig into those, I think it's time we get a bit more specific about what made AlexNet so special. What were some of the key innovations that really set it apart?
One of the biggest ones was using what's called ReLU. It stands for Rectified Linear Unit. It's a type of activation function, and without getting too technical, it basically helped the network learn much, much faster than previous methods.
Okay, back up for a second. Remind me what an activation function is. It's
Yep.
been a while since my intro to machine learning class.
Sure, it's like a little gatekeeper inside each neuron of the network. It decides whether that neuron should fire, send a signal based on the input it's receiving. And ReLU turned out to be a much more efficient gatekeeper, so the whole training process just sped up significantly.
Got it. So ReLU is like oiling the gears of the learning process. What other cool tricks did they come up with?
Well, remember how we talked about them using GPUs? They didn't just use one. They figure out how to use two GPUs at the same time, splitting the workload between them. It's like having two chefs in the kitchen working on different parts of the same dish.
That's clever.
Eh.
But I'd imagine coordinating between two GPUs must add some complexity, right?
It does, but they managed to do it really effectively. And their paper actually includes a diagram, it's figure 2 if you want to check it out, showing how they did that parallel processing. The result was a pretty noticeable reduction in error rates.
Okay, so 2 down. What's the next innovation on the list?
Next up is what they call local response normalization. It's a bit like adjusting the contrast in an image, making the important features stand out more. This helps the network learn more effectively because it's not getting distracted by irrelevant stuff.
So it's like highlighting the key parts of the image for the network to focus on. And did this actually lead to better results?
Oh, yeah, definitely. They saw some big improvements in accuracy after implementing this technique. It's all about fine-tuning the flow of information through the network.
That makes sense. Seems like all these little tweaks add up to a big performance boost.
Hmm.
What was the last trick up their sleeve?
The last one is overlapping pooling. It's a way of kind of downsampling the image data, making it smaller, but without losing the important information. It's like compressing a file, you're getting rid of some of the data, but you're keeping the essential stuff. This makes the model more efficient and also more robust.
Wait, so they're actually shrinking the image as part of the processing?
Yeah, it's a technique called pooling. Think of it like this. Instead of looking at every single pixel, you group them into little blocks, and then you take, say, the average value of all the pixels in that block. This reduces the amount of data you have to work with, but it preserves the important features.
I like that analogy.
Yeah.
And did they use specific parameters for this pooling?
They did. They used overlapping pooling regions, which actually helped them get even better accuracy compared to the standard pooling methods.
Wow, it's really impressive how they thought through every step of the process and came up with these innovative solutions. They really addressed all the potential bottlenecks.
Exactly. They had a deep understanding of both the problem they were trying to solve and the tools that were available to them. Really remarkable work.
So before we dive into the specifics of those overfitting busting techniques, data augmentation, and dropout, let's take a quick look under the hood of AlexNet itself. How many layers are we talking about here?
AlexNet has 8 layers. It's an 8-layer convolutional neural network. And that was considered pretty deep back in 2012.
8 layers, wow. Okay, walk us through it. What happens to the image data as it goes through these layers? What's the journey like?
It all starts with the image data coming in. The first 5 layers are convolutional layers, and then after that, you have 3 fully connected layers. Each layer does its own thing, extracting increasingly complex features from the image.
So it's like a hierarchy, going from simple features to more and more complex ones as you move through the layers.
Right, you start with these convolutional layers. They're really the workhorses of feature extraction. So the first convolutional layer takes the raw image data and applies filters to it, kind of like looking for certain patterns. It might be looking for edges or corners, very basic things. Then each subsequent convolutional layer builds on what the previous layer learns, so it starts detecting more and more complex patterns.
Okay, so it's like building blocks, going from simple lines and shapes to like recognizing parts of objects and then eventually whole objects.
That's a great way to put it. And then, after all that, you get to the fully connected layers. Think of those as the decision-making center of the network. They take all those high-level features that the convolutional layers have extracted, and they use that information to figure out what the image is.
Right, because the ultimate goal is to classify the image, to say, okay, this is a picture of a cat, or this is a picture of a car, or whatever it might be.
Exactly. And the very last layer, the output layer, it's called a Fosson-Way softmax. That's how AlexNet makes its final decision about which of the 1,000 object categories the image belongs to.
Wow, that's quite a journey for the image data to go through. 8 layers, all that processing. I can only imagine how computationally intensive that must have been.
It definitely pushed the limits of what was possible back then, but the results spoke for themselves. AlexNet achieved a level of accuracy on the ImageNet challenge that was just unprecedented at the time. It really showed the world what deep learning could do.
Amazing. So we've got a good sense of the overall architecture, but now let's circle back to that overfitting problem. You mentioned data augmentation and dropout as key techniques that they used. Can you break those down for us?
Sure, let's start with data augmentation. It's a really clever way to kind of artificially increase the size of your training data and also make it more diverse.
So instead of having to collect millions more images,
Right.
they're essentially creating variations of the images they already have.
Exactly. It's like showing the model different perspectives of the same object. They used a couple of techniques for this. One was image transformations, like shifting the image slightly, flipping it horizontally, things like that.
That makes sense. By subtly altering the images, they're preventing the model from just memorizing the specific pixel arrangements in the original data set.
Right. And their second technique was playing with the color. They used a method called Principal Component Analysis, PCA, to identify the main variations in color across their dataset. And then they slightly altered the color intensity of the images just to give the model a broader range of visual experiences to learn from.
That's fascinating. So data augmentation is all about giving the model more examples, but with clever twists. Now, what about dropout? How does that help with overfitting?
Dropout is a totally different approach, but equally ingenious. It involves randomly silencing some of the neurons during training.
Wait, They intentionally turn off parts of the network during training? That sounds a little counterintuitive. Why would you do that?
It might seem strange, but it's a powerful way to prevent the network from becoming too reliant on any single neuron or connection.
So it's like forcing the network to find multiple paths to the solution, to not put all its eggs in one basket.
Exactly. By randomly dropping out neurons, you're essentially creating a bunch of smaller networks within the larger network. This forces it to learn more robust and generalized features. It can't just rely on one specific pathway to get the right answer.
Okay, I see how that would make the model more adaptable. So how do they actually implement dropout in AlexNet? Do they just randomly drop out any neuron at any time?
Well, they applied it to the fully connected layers with a probability of 0.5. So each neuron in those layers had a 50-50 chance of being dropped out during each training cycle.
It's like a coin flip for each neuron, deciding whether it gets to participate or not. But wouldn't that increase the training time? If you're essentially training multiple smaller networks, that seems like it would take longer.
It does. Dropout can make training take a bit longer. But the improvement in generalization is well worth it. Without dropout, the network would be much more likely to overfit.
That's amazing. Data augmentation and dropout, two seemingly simple techniques, but they had such a huge impact on AlexNet's performance. It's really incredible how they tackle these challenges.
It really is a testament to their ingenuity and their deep understanding of neural networks. They were true pioneers in the field.
Well, I think that's a perfect place to pause for now. We've covered a lot of ground, but there's still so much more to explore.
Welcome back.
We're diving deep into AlexNet, and it's already clear this paper was a huge deal for computer vision.
It really was. We've talked about ReLU, the GPUs, and those clever ways they fought overfitting. But let's talk about the bigger picture now. How did this one paper change the whole field?
Yeah, it's easy to get lost in the details. So paint me a picture. What did computer vision look like before AlexNet?
Imagine image recognition relying mostly on, well, handcrafted features and algorithms. That was pretty much it. Stuff like support vector machines, they worked okay for some things, but they just weren't as adaptable or powerful as these deep neural networks.
So kind of like trying to build a skyscraper with just hand tools. Skilled work, but limited in what you can actually build.
Exactly. AlexNet came along like, hey, check out these awesome cranes and excavators, complete game changer.
It wasn't just academics who noticed this, right? This had to have impact outside of research labs.
For sure. Within a few years, you had companies like Google, Microsoft, Facebook, all the big names, they were all using deep neural networks. Image search, facial recognition, all sorts of things.
So those AI-powered features we use all the time, we can thank AlexNet for some of that.
In a lot of ways, yeah. AlexNet showed everyone what was possible, just unleashed a ton of innovation across the whole tech industry.
I read that error rates just plummeted after AlexNet. How big of a jump was it, really?
Yeah. Oh, it was incredible. By 2015, just 3 years after AlexNet won that ImageNet competition, error rates had dropped, like massively. For some tasks, they were getting close to human-level performance, which was unheard of before.
That's crazy. But AlexNet didn't just come out of nowhere, right? There had to be some groundwork laid before that.
Oh, absolutely. The authors themselves give credit to researchers like Jan LeCun. He did that LeNet architecture way back in the 90s. Even the whole idea of convolutional neural networks goes back to the 80s with Fukushima and his neocognitron.
So it's like a relay race, passing the torch from one generation to the next.
Exactly. AlexNet took that torch and just sprinted ahead. They took those existing ideas, refined them, added their own innovations, and then boom, showed the world how powerful deep learning could be.
And those innovations like ReLU and dropout, they didn't just fade away, did they?
Not at all. They became like standard equipment. Today, you open any deep learning book or look at how modern CNNs are built, you see those ideas from AlexNet everywhere.
Quite a legacy. They didn't just solve one problem, they created a whole new set of tools for everyone to use.
And those tools led to even more powerful models. VGNet, that one went even deeper with the layers. And then ResNet, that one tackled this problem called vanishing gradients that can happen in very deep networks.
Hold on, vanishing gradients. What's that?
It's a bit technical, but basically, as you add more and more layers to a network, sometimes the signal that's needed for learning, it gets weaker and weaker as it travels back through those layers.
So like a game of telephone, the message gets garbled as it goes around.
Yeah, kind of like that. ResNet found a clever way to work around that problem, which meant we could build even deeper, more powerful networks.
Amazing to see how fast things moved after AlexNet. It's like everyone suddenly realized, hey, deep learning is the real deal.
It was an exciting time, and AlexNet deserves a lot of credit for starting that revolution. They showed what was possible and inspired a whole new generation of researchers.
Okay, we've talked a lot about the impact on the field, the models that came after, but let's not forget about the ImageNet dataset itself. That played a big part too, right?
Huge part. ImageNet was like the fuel that powered AlexNet's success. I mean, we're talking over 14 million images, 20,000 categories. That kind of scale and variety, it was just unheard of before.
Like giving AlexNet a crash course in visual knowledge, exposing it to all the complexity of the real world.
Exactly. And that's one of the big takeaways here. You need a large and diverse data set if you want to train these deep learning models to work well in the real world. It's not just about having a fancy model, it's about giving it the right kind of data to learn from.
Like the old saying, garbage in, garbage out. Even the best model won't do well if it's trained on bad data.
Absolutely. And ImageNet set a new standard for datasets in computer vision, became the benchmark for training and evaluating new models. And it led to even bigger and more diverse datasets in other areas too.
So it was a win-win. AlexNet benefited from ImageNet, and the whole field benefited of having this massive, high-quality data set to work with.
Exactly. And that's the cool thing about science. One breakthrough leads to another, and everyone benefits.
I think we've done a great job unpacking the legacy of AlexNet. But before we wrap up, I want to take a minute to think about some of the bigger themes that have come up in our conversation.
I like that. Always good to zoom out and look at the bigger picture.
One thing that really stands out to me is like the importance of building on what others have done. We saw how AlexNet got inspiration from earlier research on convolutional neural networks and then how their innovations influenced the models that came after.
That's how science works, right? Building on the shoulders of giants, refining old ideas, pushing the boundaries a bit further.
It's a team effort, like a relay race. Each generation contributes to the overall progress.
Exactly. And it shows how important collaboration and open communication are in science. Sharing ideas, data, code, so others can build on that work and move the field forward.
Really important, especially now with technology moving so fast. We need an environment where researchers can share what they know and work together easily.
Totally agree. And that brings us to another important thing, the power of open data sets like ImageNet. Having access to these huge public data sets has changed everything for deep learning. Researchers all over the world can train and test their models on the same data, which makes progress so much faster and leads to more innovation.
It's like democratizing knowledge, right? It's not just limited to researchers who have the resources to collect their own data. Anyone with a computer and internet can be part of cutting-edge research now.
That's a great way to put it. And we're seeing this in other fields of science, too. Open data, open source software, open collaboration. It's becoming the norm, which is a good thing.
Well, I think we've covered a lot of ground in this deep dive. We've explored the technical stuff, the impact on computer vision, and some of the bigger themes that came up.
It's been fascinating. I hope our listeners are feeling inspired to learn more about deep learning and all the amazing things happening in AI.
Now, before we wrap up, I want to leave our listeners with one final thought. We've been talking about the impact of AlexNet, and it's clear that this paper was more than just like a single event.
Oh, yeah, for sure. It really set off like this whole chain reaction.
It did. And not just in terms of, specific techniques, but the whole way people approached computer vision.
That's right.
What strikes me is that AlexNet, it was a bold move at the time. They took these convolutional neural networks, which, they hadn't really been proven to work at that scale.
Right.
And they just kind of went for it.
They did. They had this, I guess, hunch that CNNs were the right tool.
Yeah.
And they were willing to really push the limits, both with the computation and the data, to see if they could make it work.
And that's a good lesson, isn't it? Sometimes you have to kind of trust your gut and take that leap.
Oh, for sure. Science isn't always about, following the well-trodden path.
Right.
Sometimes you got to forge a new one.
Yeah, and their risk, it really paid off, spectacularly. AlexNet's success kind of opened the floodgates.
It did.
All of a sudden, everyone's trying to build these deeper, more complex networks.
It was like a gold rush, but for AI.
Exactly. And all that research and development, it led to some incredible progress in just a few years.
It really did.
We saw VGGNet and then ResNet, and they both built on what AlexNet had done.
Yeah.
But they also pushed things further in new directions. It's just amazing to see how fast the field evolved after that.
It is.
Each new model would come out and it would learn from what came before, the successes, but also, the things that didn't work so well.
Yeah, totally.
But I think there's another really important lesson here, beyond just the technical innovations. It's that idea of collaboration. AlexNet wasn't just, one brilliant person working alone.
Right.
It was a team effort, building on like years of research from other people.
Absolutely.
And then it sparked this wave of like open collaboration.
Yeah.
Researchers sharing their ideas, their code, their data sets, all of that.
Yeah, that open sharing was huge. I mean, think about ImageNet. That data set was crucial to AlexNet's success. But the creation of ImageNet, that was a collaborative effort, too.
Exactly. And it's a good reminder that science really thrives when we share knowledge, when we communicate openly.
It does.
We need to keep breaking down those barriers and encourage people to work together.
Especially with all the big challenges we're facing today. Climate change, disease, all these complex problems.
Yeah.
We need people from different fields working together.
Right. So in a way, the legacy of AlexNet goes beyond just computer vision.
It does.
It's really about like human ingenuity, the potential we have when we work together.
That's a good point.
It's an inspiring story.
It is.
And it makes me hopeful about the future, you know.
Me too.
We've seen what's possible when we put our minds together.
Absolutely.
And who knows what other amazing discoveries are out there just waiting to be found.
Right. Maybe some of our listeners will be the ones making those discoveries.
Maybe. So, to everyone listening, keep exploring, keep learning, keep pushing the boundaries.
Yeah.
The future of AI is wide open. And on that note, I think it's time to wrap things up.
Sounds good.
Thanks for joining us on this deep dive into AlexNet. Until next time, keep diving deep into the world of knowledge.
Yeah.
Goodbye.